Okay, so in this video I want to talk about electrical conduction and Ohm's law, how we can make sense of electrical conduction in a conductor, like a copper conductor, and also derive and make sense of Ohm's law. So let's imagine here a conductor. So this is a wire. Let's draw a thick wire here going into the screen, and let me draw this wire. Let me draw a circle here. Let me try to make, yeah, okay, a circle here. And so this is a round conductor, symmetrically circular conductor, and it has a radius r here, and this is an area a. So the area of this circle is a. Let me finish it here, and let's imagine that this conductor has a length l, and let's imagine that there is a constant voltage difference between these 2 points. So from this point here to this point here, we have a constant voltage or potential difference V. And what happens inside this conductor? Electrons flow inside this conductor and make up a current that is going to flow inside this conductor. And let's say that this current is flowing on this direction here, so out of the wire and perpendicular to this surface here, to this circular surface. So this is what we have. We have a conductor, electrons flowing this way. And now the first concept that I want to clear up and introduce is the current density. So the current density vector that we call J, and this is equal to sigma times the electric field E. And let me clarify what this means. First of all, this current density means the amount of current flowing into this conductor divided by the area here. So this is what it means, and this can also be written. So J is equal to, so it's the current divided by the area. Let me correct this. So it's the current divided by the cross-sectional area of the conductor. So imagine there's a current flowing here, and this is the area. We divide by the amount of current by the area, and this is the current density. Now the current is also equal to the number of electrons n times the electron charge E minus divided by a certain time t, and we also have a. So n E minus divided by t is equal to I, which is the current, which is simply the amount of charge divided by time. So n times E minus is the number of electrons times the charge of an electron, of a single electron, and this is a certain amount of time that we measure the number of electrons passing through this point. So this is going to be the current. So then we have that J is equal to I over A, and this is simply equal to n E minus over AT. So n E minus is charge, T is equal to time, A is equal to the area, I is equal to the current. So we know that J is equal to this, but J is also equal to sigma times E, which is the electric field. Now sigma is called conductivity, and the conductivity is a constant that varies depending on the conductor. For example, if you have a copper conductor, it's going to have a certain conductivity. And for example, for copper, let's write down here for copper wires, the conductivity is equal to 5.8 times 10 to the 7, and this is given in a unit that is called Siemens per meter. This is not very important, I'm just giving it for completeness but this is what it is. This is the conductivity. So J then, again, J is equal to sigma conductivity times the electric field. So the second thing to clarify is, what is this electric field? The electric field is, if you take a normal conductor without a battery attached to it, without any voltage, there is no electric field there, because there is no conduction, there is no voltage, so the electrons will not move in a certain direction. They will not conduct electricity. If you apply a voltage between the 2 points on the conductor, then you are creating a potential difference. So electrons will flow from the higher that we also call plus to the minus, to the lower potential. And it's like if you have a well like this and you put a ball here, the ball will flow from the higher potential to the lower potential under gravity. So it's exactly the same for electricity. If you have a higher voltage and a lower voltage here, the electrons will flow from the higher to the lower. So when the electrons flow like this, there must be an electric field pushing the electrons in this direction. Just like we have gravity, if you have a ball here and you have the floor here, there is a force of gravity pushing the electron, pushing the ball downwards. And the electrical force is exactly like the gravitational force. If you apply a potential difference, there will be an electric field pushing the electrons. So let's clarify how the electric field works. Suppose I have a charge here, I have a proton here, plus have a charge here in space. There is nothing else around the charge. This charge is going to create an electric field which points radially outwards like this around the charge. So there are lots of vectors here in space. For every point in space we have a vector pointing outwards from the charge. And this means that if we put another charge here, let's call this charge Q, and let's call this charge Q1. If we put a charge here, this charge is going to exert a force on this charge in this direction. So this charge is going to push this force. This is going to push this charge here in that direction, and there will be a force between them. Let's call the distance between these two charges here, let's call this distance R, and let's call the force pushing the charge F. Let's call the force F, and the force is a vector, so we write an arrow on top of it, and the vector is pointing in this direction. So how do we define the electric field at this point? We know that Coulomb's law say that the force is equal to a constant K times Q1, which is this, times Q2, which is the second charge, which is this one, I'll just write Q, divided by the distance between them squared. So if you have two charges like this, the force is going to be equal to K times the first charge times the second charge divided by the distance between them squared. So this is the force. So if we know the force here for this amount of charge, we can calculate the force for just 1 coulomb of charge. Instead of having lots of protons here, we can calculate the force for just one proton, just one positive charge. And to do this, we define this to be the electric field, and this is equal to exactly the same, K times Q, which is this charge here, and we divide by Q1. So it's simply equal to K times Q times R squared. We divide by Q1 here. So if there's a Q1 here, we divide here by Q1, so this cancels. So this is equal to the electric field. So the electric field is also a vector, which also points in the same direction here, which is equal to the constant K times your charge Q1 divided by R squared. And also let's consider the unit vector from this charge to here, and let's call this unit vector R hat. So this is times R hat. You can forget about this for now, this R hat, so actually I'll just not write it right now. So this is equal to this. So this is what the electric field is and what it means. So let's go back to this formula. J is equal to the conductivity times the electric field. So J is equal to conductivity times the electric field, and these are just the magnitudes. So current density is equal to conductivity times the electric field. So that means that if you have a conductor, again, then the amount of current, the current density is going to be proportional to the electric field. So there's going to be an electric field in some direction, and depending on how conductive the conductor is, you're going to have more current or less current. So this is all this means. Now the second thing we need to understand is what voltage is in terms of electric field. So again, let's suppose we have a charge here, plus, and we have another charge here, plus. Let's call this Q1 and this is Q, and there's a distance R between them, and there's a force in this direction. So let's calculate the amount of work that we need in order to push this charge from infinity. So suppose we have infinity here is a long distance. We want to push this charge from infinity up to this point. And this is because we take infinity to be a reference point. We want to calculate the work necessary to push the charge from infinity up to this point here. Infinity is a very convenient point to have, because any other point is going to give you a constant. And you cannot calculate it from the first charge. Okay, so infinity is a very good reference point to have. So we want to calculate the work, the amount of work necessary to bring the charge from infinity up to this point. And that's what voltage means. Voltage means work, and so voltage means energy or work per charge. So you want to take a charge from infinity and bring it here and calculate how much work that needs to take. So this is what voltage means. So in order to calculate this, we need to calculate an integral, and we write this like this. So this is an integral on a path C, which means the path from infinity to this point, which is just a straight line in this case. And we calculate that, which is going to be equal to the force at each point here. And actually I'll write this as the electric field, because we'll do it just for 1 coulomb of charge. And we dot this with dr, which is an infinitesimal vector at each point here. And this is going to be equal to the voltage difference, or the work to bring charge, or 1 coulomb of charge from infinity to a point let's say r prime. So if we do this, then we'll know the voltage between these 2 points, and we'll know the amount of work. Now we want to do this for conductors. So we want to do this for a conductor. We want to bring the charge from one point in the conductor to another one, and the amount of work that we do is going to be equal to the voltage. Now let's suppose that the electric field from this point, between this point and this point, is a constant. So the electric field is simply equal to the constant E. So, and the distance here from one point to the other is R. So this integral here is simply going to be equal to E dot I'll substitute dr for dx or dr, just a simple constant dr, because the vector has only one direction here. So this is simply going to be equal to E times R, which is the electric field, the value of the electric field, times R, which is the distance between these 2 points. So this is also equal to the voltage from this point to this point. And I did all this just so we can write that the voltage is equal to the electric field, the electric field is equal to the voltage divided by L, the voltage divided by R. So all I did all this just so we can write that the electric field is equal to the voltage divided by the distance. So from this point we can derive Ohm's law. So let's just rewrite this. We know that J is equal to I divided by A, and we also know that this is equal to sigma times the electric field, and we know from all this that this is equal to the voltage. This is equal to sigma times the voltage divided by R. So from this we want to derive Ohm's law. So this means that I divided by A is equal to sigma times V over R, and so I is going to be equal to sigma times the voltage times A divided by R, and now we can divide top and bottom by sigma times A, so this is equal to V over R divided by sigma times A, and again this is equal to I, the current I. Now we'll call this term here R divided by sigma A. This we'll call the resistance R. So from all this we get that V over R is equal to I, or V is equal to I times R, and of course this here is our familiar Ohm's law. Ohm's law that we have just derived in this way. So I have done all this just so we can derive Ohm's law from first principles, and so that we can understand how current works in a wire. And so let's have a look at this term here, R, which is equal to R divided by sigma A, and again sigma is equal to conductivity. There's also another term called rho, which is equal to 1 over sigma, and this is called the resistivity. Now the resistivity is also dependent on the material you're working with, just like the conductivity. Some materials have higher resistivity and some others have lower resistivity. So let's suppose we have a conductor here, a piece of material, and this has a length L and area A, and there's a current flowing in here, and it offers a resistance R for the current. So there's also a potential difference V between these 2 points, a current I flowing in here, and a resistance R. So let's work with rho. So rho is equal to 1 over sigma, which is equal to so let me first write down sigma in terms of the resistance. So sigma is equal to L or R over R times A. So this is what sigma is, and this is the conductivity. So rho is 1 over the conductivity, so this is equal to R times A over L. So R times A over L is equal to the resistivity, and so we look at this conductor here. How does this resistivity make sense? Let's suppose that for a resistivity rho we have a certain resistance R, and we multiply that by the area and divide by the length. So this is what the resistivity means, the resistance times the area divided by the length. So let me write it down here again. So rho is equal to R times A over L. And let's suppose the length increases. If we increase the length of the conductor, but the resistance is still the same, then this L here is going to make this number smaller, and by consequence the resistivity is going to be a smaller number. And this makes sense because if you increase the length of the conductor but the resistance is constant, then that must mean that there is an intrinsic property of the conductor which makes it have less resistivity. In a similar way, if we increase the area of the conductor, let's say this area here is greater and the resistance is the same, then that must mean that the resistivity is higher. And that will be true because A here is going to be a larger number, so rho is going to be a larger number and the resistivity is going to be larger. So this is basically how resistivity works, and I'll stop here for now, and thank you very much for watching.